Okay, let's get ourselves started. To get us started for today, first, calendar. You also see that while I'm recording, I actually use like a louder voice just to make sure that the microphone's picking me up. So it might seem like I'm talking loud today, but I am. First things first, calendar. Yesterday, first couple times it'll be funny. Yesterday, we went over a couple more problems dealing with acceleration of gravity. We talked about your lab and how the graphs relate to the motion of that object, how we can identify certain parts of the flight of that object based on the mostly the velocity graph. The velocity graph is the easiest one to read. So we talked about that. Hopefully you got your graphs labeled. I think pretty much every analysis question that was on your lab, we pretty much discussed somehow, some way in the course of our discussion yesterday. So hopefully you got that taken care of. You can get that lab turned in sometime in the relatively near future, if not today. Today, last bit of new information for your test, which is scheduled for Friday. Tomorrow, I have a review activity planned for us that is somewhat fun, but it is useful as far as reviewing topics and stuff like that. We are going to watch some movies tomorrow, some actual real movies, not like Bill Nye, all right, like some actual, like, not Avatar. So, although Avatar might, not for this section, Avatar won't work. But, there's one Star Wars movie, Return of the Jedi, it's part of Return of the Jedi. GoldenEye, that's clips. We will watch parts of the movie and then discuss some of them. So it's usually a pretty good day. It seems that from our discussion that it helped, or from my discussion of previous years, it helps. And there's also a day where we will watch some movies in the next chapter too to discuss some topics there. So it's good for us to look at some things, find out what's good, what's bad, why is it good, why is it bad. Good review, not only, so there's concepts part, but there's also some problems that go along with it. So give you some review on both sides. And then test on Friday over Unit 3, kinematic equations, acceleration of gravity, and relative velocity. If you go back to the home page and you go to objectives and homework sheet, Unit 3, kinematic equations, acceleration of gravity, relative velocity. So there's objectives sheet there. You'll notice if you open up the objective sheet, that there really aren't that many objectives. There's only 4. A lot of the stuff that we did in this class, or in this unit, we did a lot of problems to begin with, so kinematic equation problems. Then, the second one that says analyze the motion of an object moving under the influence of gravity, that was basically your quiz from yesterday. Our discussion about the lab from the graphs and all that all is encompassed within analyzing the motion of the object under the influence of gravity. Use acceleration of gravity, 9.81, in the kinematic equations. We've done that before. And then analyze the motion of an object moving in one dimension from different frames of reference. That's what we're going to do today. There are some problems from the book, okay? But this last section on relative velocity, which we're going to start with today, there really aren't that many problems from the book, so there are a bunch of problems listed here on the objective sheet. And I'll show you where to go with that a little bit later on. Seems like a lot of problems. Really, we're covering this for one day, right? So the focus on the test is not going to be as much as some of the other things we've covered. Okay? So keep that in mind. Not that you shouldn't pay attention, but all right. With that being said, here. I printed out some slides for you today, important things that we're going to cover, some problem-y type things that we'll talk about, so you've got pictures in front of you and you can go from there. All right. Starting off, let's review a couple of terms. Okay. Position. Position. How do we define position? Explain to me position. Oh, I know, class participation. Okay, go ahead. Distance from the reference point. Not just distance from the reference point. No. Okay. Position being a vector quantity, right? You have to give me some distance and direction from the reference point, right? Or our location relative to our reference point, okay? Displacement. our definition of displacement. Final position minus initial position. So our change in position from start to finish. Okay? Velocity. Speed with the direction, yes, that is good. As far as calculating velocity, what do we need to know? Displacement over time, so the change in position over the time frame over which it occurs. Okay. Let's go. Relative velocity. Velocity is a vector quantity. Hopefully we all got that. We all remember that, right? Vector quantity meaning that it tells us what? Let's go more generally, magnitude and direction, right? How big, which way. And then, sure, like you said, that in this case that would be speed, how fast it's going, and then whichever direction. But how it's measured depends on our frame of reference, right? Our frame of reference needs to include two things. What does our frame of reference include for us? A reference point, and then a directional system, right? Which way we're going to call positive, which way we're going to call negative. Right? Velocity can change depending on how we measure that velocity or from what frame of reference. Think of the question about the hill people and the valley people from the previous test, right? How we measure something depends on where we reference it from. What's our reference point? What's our up? What's our down? Et cetera, et cetera, et cetera. Okay? And the gist of that being, two people might look at something differently depending on where we look at it from. Is it a different motion? No, it's not a different motion, but how we describe it, how we represent it could be different based on where we're looking at it from, how we reference it, et cetera, et cetera, et cetera. All right, a couple more things here, and we'll get on to some examples. Frame of reference, right? When making measurements of the physical world, reference point and directional system have to be chosen. Hopefully this is all stuff we know, and we just discussed it like 2 minutes ago. All measurements are made from this reference point and within its directional system. And that's how we measure stuff. And we've talked about, like the last test, we talked there was that, like I said, the question about the hill people and the valley people. We've talked about when we use the motion detector, the frame of reference is chosen for us. We have to make sure that we keep that in mind as we're reading those graphs, interpreting those graphs, et cetera, et cetera, et cetera. Frame of reference does not always have to be stationary, however, and that's what we're going to talk a little bit more about today. For example, so here's a picture of various objects in motion. Okay? So let's say we have this car here. Right, down here at the bottom. And if you ask the person in the car, now here's something, sorry, before we reference that, or before we start that, we have to keep in mind that how we define velocity, how we define position is relative to our reference point. So some of the things that we may talk about today might seem weird, might seem like, hey, no, that's not really happening. But if you look at the measurements, that's really what those measurements are telling you. Okay? For instance, guy in the car, right? If he looks at, let's say, this tree down here at the bottom of the screen, okay, measures its position at a certain time, measures its position again a little bit later time, what would his measurements tell him that tree is doing? Getting closer to him. Which way is that tree moving, at least relative to him? It's moving in the negative direction, right, towards him, but as far as the directional system goes, it would be in the negative direction, right? If, out of here, sorry, I should have done this before. Open that by. Stand by. Totally. Probably just sound like a mumble at this point, but what? a lot of times when I'm making my videos, I have to do this because I forget to like open stuff up, but I've been better about editing it out so I don't see all this stuff. So. All right, let's go here. Road. Right. Shush. Car. With apparently a broken axle. So it's real. Yes. Yeah. Okay, so there's that tree, right? Okay. If we ask this guy to make a measurement of that tree, most likely, what's the reference point going to be? Where he's sitting, right? So we're going to call this the reference point. And just for simplicity's sake, why don't we say that this is the positive direction and this is the negative direction? Okay? So he makes a measurement of that tree. Let's say he makes a measurement of that tree, and that tree is 10 meters in front of him, so he calls the position of that tree positive 10 meters. Yes? A couple seconds later, he's driving along. All right, let's see if this will work. It's a hovercraft now. So, all right. At least the wheels stick together. So, all right. So, now the car has moved. Right. The guy really doesn't see that, though, right? What is the reference point still for this guy? It's still him, right? So if we change, right, and we call this our new reference point, right? Positive direction still this way, negative direction still this way. Now the tree is only at a positive 5 meters position, right? Displacement, calculating the displacement of this object, delta x equals x final minus x initial, right? The final position minus the initial position. When you plug in the numbers we just memorized, or that we just looked at here, what's the displacement of that object? Negative 5. Does that make sense? Okay. So according to that guy, which way is the tree moving? In the negative direction. Is the tree actually moving? Answer is, depends on who you ask. Right? There's no difference in how this guy measures motion if he's moving forward or whether the tree's moving backwards. But according to his measurements, right, we end up with a displacement of negative 5. If we ask the tree, right, we'd see the car is moving in that direction. How far? 5 meters. Direction depends on the frame of reference of the tree. The motion's not any different, but how we describe it is. Does that make sense? If we go back to this picture, grab this, and draw it. If you ask somebody in this car, right, what's the plane doing? Right? That plane is moving positively. Right? But, as you know, the guy in the car sees the plane start here, and the plane ends up over here. Right? But if you ask somebody in the plane, what's the car doing? Moving backwards. Any difference in the motion? No, but how we describe it depends on our frame of reference. Moving frame of reference, we really can't tell whether one thing's moving and one thing's sitting still. It all just depends on where we describe it from. So if you look at the car, does that make sense or not?
All I heard was the noise.
So, Rachel, if you're in the plane, right, you see that car. If you're in the plane, well, my battery died? If you're in the plane, the car starts out in front of you, right? But as you're flying, where does the car end up? Behind you. Is the car moving backwards? not according to you in the plane, or not according to the car itself, right? But if you make the measurements of where it is at the beginning and where it is at the end from the plane, right, that car was moving backwards. Good there? Another example. Anyway. So, that's a cool animation. Oh, it was a really cool animation. It was a crappy animation, but illustrate that point. Okay. So, two cars, right? Car A moving along, car B obviously moving faster than car A. How can I tell? Look at these tremendous whoosh lines that are back here, right? I mean, car B is booking, all right? So, if you look, right, these motions get described differently depending on who we ask. If you ask this lady standing here with her dog watching these cars go by, she says car A is moving to the right at a certain speed, car B is moving to the right at a faster speed. All right? But if you ask car A, does car A see car B moving forward or moving to the right in this picture? Yeah, okay, because it's going faster. Would car A measure its velocity as fast as this lady would? B. If we ask the lady what car B's velocity is, and we ask the guy in car A what car B's velocity is, would they give you the same answer?
No.
They wouldn't, right? Not because car B's motion is different, right? But it's from a different frame of reference. Remember that velocity depends on how far you go, displacement, divided by the time it takes you to go that far. Okay? Let's say, to start off, I'm going to do this. First I want my board to work, but other than that, let's say to start off, the car B starts, I don't know, let's make something easy, 10 meters away from the lady, right? And based on where car A is in that time, right, how far away is car B from car A?
7.
Car A and the lady look kind of close to the same spot, right? Okay. So, right, this is also 10 meters. Okay. Let's take a look 1 second later. Right? 1 second later, sorry, I should have thought this out a little bit more. Okay. Let's take a look 2 seconds later. Okay. 2 seconds later now, right? What? 2 seconds later, car B is now 10 meters past the lady. Does that make sense? Okay. But where is car B if you ask car A? Right next to it. So in that 2 second time interval, how far has the lady seen the car go? 20 meters. But in that 2 second time interval, how far has car A seen that car go? Only 10 meters. Not because the motion is different, right? Just where we measure it from. Does that make sense? Now, when we start looking at numbers here, okay, let's not get confused. It may seem a little confusing here, but when you start looking at numbers, I really think of it as more of a common sense sort of thing. With that in mind, let's go here. Okay. So, this is on the back of your sheet, by the way, all these colors.
Oh, jeez.
A fish is swimming in water at 2 meters per second. The current is moving in the same direction as the fish at 1.5 meters per second. What is the velocity of the fish as seen by a person sitting on the dock? So, this is pretty straightforward, at least I think it is, but let's just draw a picture just to make sure. Okay, let's go here, let's go here. Let's go here. Right. So there's your picture. Now there's your problem. Ooh, something's wrong over there with my calibration. There's my dock. There's my person sitting on the dock. Right? Water, whoa, is moving this way 1.5 meters per second. Yeah, kind of looks like 13. Apparently there's something wrong with my calibration down here at the bottom of the screen. Top of the screen works just fine, which I suppose means I could just do this. This work. Just part of my dock. My person. Move my water up. There we go. Alright, so water is moving at 1.5 meters per second this way. Okay?
Big.
Yeah, it's huge. It's huge. It's like the Moby Dick of physics class right there. So, alright. But the fish can swim at 2 meters per second. Okay? So, if you ask this guy on the dock, what's he going to see about the fish? How fast is that fish going to be going? 3.5 meters per second. Which way in this case?
That way.
That way, right? To the right. Okay? Positive, whatever. Okay? Good there? That makes sense? Next. Wow, this really needs to be recalibrated, but... Alright. Whoa. If you watch this at home, it's going to make you dizzy. Alright. What is the velocity of the fish as seen by a person sitting in a rowboat that is floating with the current? Okay. Water. Boat. Right. We know that the water is going this way at, oh, not 2. 1.5, right? At 1.5 meters per second, and that the fish can go 2 meters per second in that same direction. But what's the boat doing? Moving, right? The boat is also going at 1.5 meters per second in this direction. Does the boat see the effect of the water? The boat doesn't see the effect of the water. So it sees the fish going at 2 meters per second. Is there any difference in the motion of the fish as seen by the dock or the guy in the boat? The motion is exactly the same. But what's different? Point of reference, how we measure it, how we represent it. Good there? What's the velocity of the fish as seen by a person in a motorboat that is traveling in the same direction as the current but can move on its own at 15 meters per second? Good question. Ooh. Good question. Billy, phrase it again for me.
Motorboat go with the current.
Okay. So the motorboat is traveling in the same direction as the current, right? It says that in the problem. So, boat, now it has a motor on the back of it, right? A propeller in the water, right? Person in motorboat. It's a different guy, because he's got, you know. So it's our fish, right? Water, 1.5 meters per second. Fish, 2 meters per second. Boats, 15 meters per second. Person in the boat is going to see the fish moving at negative 13.
Wait,
Okay.
after seconds.
What?
After seconds.
Say again?
Okay.
So, the velocity of the fish as seen by a person in a motorboat that is traveling in the same direction as the current, but can move on its own at 15 meters per second. The right answer here is negative 13 meters per second. Do we understand why?
Yes.
So, let's talk about why. Right? This boat is traveling in the same direction as the water and the fish. Okay? Is the water helping the fish? Yes. Is the water helping the boat? Yes. So we can pretty much neglect the water. Right? It's really not doing anything in this case because both of these objects are feeling the effect of the water. So now let's just focus on this, right? Go back to the airplane and the car from one of the pictures we looked at before. If the guy in the boat sees the fish there, out in front of him, right? Okay. But what's he going to do? How fast are they going? Who's going faster? The boat's going faster. So where's the fish going to end up? Behind the boat, right? If we look at these velocities, right, the boat can go 15 meters per second on its own. The fish can go 2 meters per second. There's a difference there of 13 meters per second. So the guy sees the fish moving backwards at a rate of 13 meters per second. Billy, go ahead.
So, what I was asking earlier is, if we're going to get this on a cruiser of some sort, it would be after 1 second of the last.
I mean, you could look at it that way, Billy. If we did that, we could plug numbers in and find a displacement and find the displacement of the fish relative to the boat and stuff like that. We could do that, but in this case here, if it's just asking you about the velocity, let's just look at the velocities of those objects and kind of go, okay, boat's going forward, fish is going forward, but boat is going faster than fish, so he's going to see the fish moving backwards. Okay, that's why I said this section. I really like to approach it more from a common sense standpoint than a mathematical standpoint. As a result, these questions on the test are not going to be calculation problems. They're going to be short answer problem, multiple choice problem, something like that. Okay. Are we good with this one? After the explanation? So good. So good. All right. Fish swimming in water at 2 meters per second. Fish is swimming against the current, moving at 1.5 meters per second. What is the velocity of the fish as seen by a person sitting on the dock? Water, dock, guy sitting on dock, right? Fish. Fish can go 2 meters per second on his own, right? But current, 1.5 meters per second, but in the opposite direction. So what's this guy who's stationary going to see?
Thank you, Jason.
If we decide what? We decide the way the fish is going is possible. Good there? Velocity of the fish, as seen by a person sitting in a rowboat floating with the current. That's rowboat guy. Giant goldfish. So, Fish going this way. Oh. Fish going this way.
Really get that.
2 meters per second. You have to recalibrate. Water going this way. 1.5 meters per second. Okay. If the boat is just sitting in the water, right? The boat's just sitting in water. Boat also going 1.5 meters per second that way. So how fast does he see the fish going?
0.5 meters per second. Yeah, which way is negative 5?
What?
He's going away from the current. Current affects him.
Let's get a Reddit 2. Reddit 2.
Alright, he's saying about it.
2.
Get money.
The water is pushing the boat. Wait, no, my bad.
Yeah.
Yeah,
That's
yeah.
back.
Change it. Yeah.
My bad.
It's 0.5.
Does
Hey, yeah.
does okay? So frame of reference. Which way do we want to be positive here? These are the guy in the boat. Is the way he going positive?
Negative. No, it's not negative.
He's going negative.
Yeah.
So negative this way, positive this way. So I mean, okay. Is the fish being affected by the water?
Yes.
Yes. Is the boat being affected by the water?
Yes.
Yes. It is the water, right? So, do we see the effect of the water in either case?
No. What? Yeah. I mean,
Kind of.
Like not you can go to so pretty much. I'm gonna have a headache all day.
Love when that's alright. So, the fish is going slower because of the water, right? If you ask somebody who's standing over on the side. But here, right, this guy's going with the water in this direction. Okay? But the water is also affecting the fish. Yes? Okay?
All this.
Freestyle. You lost. You lost.
Oh, because they canceled.
Why did you tell us that Joe was
What?
Yeah, what was the significance of time?
So you knew that I was recording class today?
So we wouldn't accidentally.
So I wasn't just secretly recording you? Full disclosure, I was recording you in class today. So. And now you can go. Alright, one more.
So we like really make fun of them and finding out.
Oh, nope, that was it.
Yeah.
Alright, so.
Pause the recording.
Let's wrap this up real quick. As far as relative velocity goes, where we measure stuff from will affect our description of it, right? There can be a change in the measurement of a motion based on its reference point. Not necessarily that the motion is changing, but how we represent it that's changing. Okay? And, like I said, I like to do it more from a common sense standpoint as opposed to a mathematical formula or something like that. Look at the factors that are going on there, decide how is this person going to see it, how is that person going to see it. Okay? Like I said, we've spent one day on this, and that's the end of it. Is it going to be a big part of your test? Yes, it's going to be your test. Okay? There will be some questions on it, not calculation questions, or multiple choice short answer questions. Okay. Questions before we get done. All right. For tonight, if you look on the calendar, there is a link down there at the bottom that says answers to relative velocity problems from objective homework sheet. The objective homework sheet that I showed you at the beginning of class, that there are a bunch of relative velocity problems on it. All the answers to those problems are posted online. However, it's just answers. I didn't show you work. So you can check it out. Okay? Tomorrow we review. Test on Friday. Start looking at some review stuff. Probably a good idea.
Yes, sir.